Hey everybody, today we will take a new approach to the atom. We are going to talk about the quantum mechanical model and quantum numbers. And just a heads up, things are gonna get weird, and we will try to cycle back at the end of the video and make sense of it all, but don't get upset or don't get discouraged if things don't work out the first time around. This is something that we need to revisit constantly to try to make sense of because it's pretty unlike anything we've really ever seen. So we have seen thus far the Bohr model. The Bohr model is the one where you draw the nucleus in the middle, right? And then you draw all of the different rings and you put electrons on the rings and they have these very fixed orbits with energies. But it turns out that that wasn't really working because we need to incorporate this idea of waves into that and also probability. And so there are three scientists who are working on this. We've talked about Heisenberg, we've talked about de Broglie, and now we're going to bring in Erwin Schrödinger. Schrödinger is probably thought of as the father of quantum mechanics. He did much of the math that we're about to look at. So let's jump back for a second. We know that electrons behave both as a particle and a wave, and so this new model focuses primarily on the electrons. We're going to treat the nucleus as this positively charged thing in the middle of the atom. That's not going to change, but the electrons are what we're going to study in depth with this new model of the atom. And so the quantum mechanical model is a mathematical model, and it's a crazy looking formula. So you might want to do yourself a favor and pause the video and look up online something called Schrodinger's Equation. And you're going to see some fun symbols that you've never even seen before, and it's not going to look anything like math, but that is the equation that is kind of the backbone of our current understanding of the atom, also known as the quantum mechanical model. So that equation that you can look up online and you can, take a picture of if you so desire, it has some solutions. And basically the solutions are if you look at a given electron in an atom. So for instance, we know something like hydrogen has one proton. It would then have one electron to cancel out the charge in a neutral atom. That one electron has solutions in Schrodinger's equation. And if you solve Schrodinger's equation for that specific electron, you're going to get a value for four different numbers, we'll say. So there's a quantum number called n, there's a quantum number called L, there's a quantum number called M sub L, and a quantum number called M sub S. And you can see those on your note guide. So that one electron for hydrogen, it has solutions for all four of those quantum numbers. And those quantum numbers are what we're going to discuss today. So first off, remember back to the uncertainty principle, it's really hard to know exactly where something is and how fast it's going in the format of electron. In fact, you can't do it, right? So what we actually are going to do is do this based on probability. And so what we're going to do is put the nucleus in the middle. You can imagine the middle of this coordinate axis, that little green dot that I drew, that is the nucleus. And we are going to predict the likelihood of finding an electron in certain areas around the nucleus. And those certain areas, we call those orbitals. Looks a lot like orbit, but it's not these concentric, nice circular orbits. Instead, it's these three-dimensional shapes or volumes where we might expect to find electrons. If there's a really high likelihood of finding it there, we would say that it has high electron density. If there's a low likelihood of finding electrons somewhere, we'd say it has low electron density. Okay, so when we solve Schrodinger's equation, we get these four quantum numbers. And we're going to talk about each one individually, then I'm going to sketch them out for you in a format that hopefully makes more sense to us. So the first quantum number is called the principal quantum number. It is denoted by an italicized lowercase n. It is the energy level. So if you remember when we numbered off the periodic table, hydrogen and helium are in energy level 1, and so on as you go down the left-hand side of the periodic table. So the energy level is corresponding to the quantum number lowercase n. That one's probably the most straightforward. Down here, it says it correctly on your note guide, but the number of orbitals in each energy level is equal to not n times 2, it is n squared. So if you're wondering how many orbitals are there in the second energy level, it's 2 squared, it's 4. And again, we'll see that a little later on. The next one is an italicized lowercase l. Let me box that a little better. italicized lowercase l, this is the angular momentum quantum number. So the angular momentum quantum number describes the shape of orbitals, and it turns out that we give this both a set of numbers as well as a set of letters. And there's this weird thing down here where it says the values of L begin at 0 and increase to n minus 1. What that means is that if your n is 1, 1 minus 1 is 0, so the value of L is always 0. If your n is 2, you have two values of L. You have 0, because we always begin at 0, and we go all the way to n minus 1. 2 minus 1 is 1, so you have 0 and 1, and so forth. If we go to 3, you have 0, you have 1, you have 2. So it always goes up to one number less than the value of n. And it turns out that these numbers also have letters associated with them. So for L, if L equals 0, we're going to call that letter S. And go ahead and write this down on your note guide. If L equals 1, we're going to call that P. If L equals 2, we're going to call that D. If L equals 3, we'll call that F. And if L equals 4, we'll call that G, etc. Actually, we'll only really get to this point, to L equals 3. But if you go beyond that, it turns out that you just follow the alphabet. So 5 would be H, 6 would be I, etc. You just follow those letters of the alphabet. The next quantum number is m sub L. Let me rewrite this. This should be m sub italicized L. That is called the magnetic quantum number. This gives the 3D orientation of each orbital. So for instance, let's talk about the p orbitals. There are 3 p orbitals, and we'll assign numbers to these, but just for right now, trust that there are 3 p orbitals. If you imagine a coordinate axis that has an x and a y and also a z, we could draw ourselves a p orbital, happens to be shaped like a peanut. We could draw ourselves a p orbital on the y-axis. We could draw ourselves a p orbital on the x-axis. We could draw ourselves a p orbital on the z-axis, like so. And so those are 3 different orientations of the same shape, right? The shape is the same every time. It's kind of this infinity symbol, peanut-shaped thing that I'm not drawing very well at the moment. Let me redraw that, in fact. But you have these 2 equal lobes, and it's this area where you might find electrons. So if you orient that in 3 different orientations in space, then that's where you get your 3 different values for m sub L. Again, I'll write these out in a minute. The final one is m sub S. So m sub S is the magnetic spin quantum number. It can have 2 values. It can have either positive 1/2 or negative 1/2. And we are going to basically represent that with arrows. And our arrows will represent electrons. So electrons that have a positive 1/2 spin, we are going to point up. And electrons that have a negative 1/2 spin, we're going to point down. And so basically in any orbital, you're only allowed 2 electrons, and they have to spin in opposite directions. So, a lot of craziness going on there. Let's dive in. Let's see if we can make sense of this a little bit better. So, let's start with energy level, right? And I'm going to define in each one of these energy levels the other possible quantum numbers. So we said n is the principal quantum number. This is the energy level. So let's start in the first energy level, right? N is equal to 1. What do we have going on there for L? Well, in the first energy level, we said that L is going to be starting at 0 and going to a value of n minus 1. So let me just put in parentheses here, n minus 1. And so L, if it starts at 0, the only value for L here has to be 0, right? Because 1 minus 1 is 0. There's nowhere else for us to go. And we can contrast that with what happens in the second energy level. So in the second energy level, we're going to start with 0. But then we also have energy level, or I'm sorry, we have L with a value of 1, right? Because we're in energy level 2. So 2 minus 1 is 1. So there are 2 values of L in the second energy level. And we can expand that further. Let's do m sub L, but before we do, one little side note, remember that L also has a number that or a letter that corresponds with it. So anytime L equals 0, we're going to call that letter S. Anytime L equals 0, we're going to call that letter S. Anytime L equals 1, we're going to call that letter P. So let me keep those in the same color as well for you. Let's now do m sub L. So m sub L, pick another color, let's go blue. M sub L has some different values, right? M sub L, we didn't talk about very much in the notes that we just looked at, but it turns out M sub L can range from positive L to negative L. So if L equals 0, positive 0 and negative 0 isn't really a thing. So M sub L in an s orbital always equals 0, because positive 0 and negative 0 are the exact same thing. So M sub L for an s orbital is going to be 0. M sub L, remember, is the 3D orientation, and it turns out that S is spherically shaped. So that's why M sub L is 0. There's not much you can do with that, right? Like, you can't reorientate a sphere and have it be different. It's always going to be the same, even if you spin it. So let's talk about what this is going to look like in energy level 2. So again, for the S, we have 0. Let me write this like so. And then for P, so S is 0. For P, we're going to go from positive L to negative L. So remember, L has values of 0 and 1. We are going to put in the numbers -1, 0, and 1. So we went from positive L, that's that 1, to negative L, that's the negative 1. And then M sub S for each one of these is going to be plus or minus 1/2. And it turns out that plus or minus 1/2 actually represents 2 electrons. Remember how we drew this? We said that positive 1/2 goes up, negative 1/2 goes down. So what that means is that in this one little orbital, we can fit 2 electrons. We can fit one facing up and one facing down. Over here, we again have plus or minus 1/2, but you'll notice there are 4 orbitals. So in the -1 orbital, we can go up and down. In the 0 orbital, we can go up and down. And in this orbital, we can go up and down. And it turns out, actually, that this orbital that we've drawn here is actually this one over here. So as we look at our energy levels, and I know this is getting rather convoluted rather quickly, if you look at the periodic table, you have different energy levels, first, second, third, etc. As you go down, those are the horizontal groups on the periodic table. And so even though we're looking at the second energy level, the second energy level is the one that starts with lithium, right? So in the second energy level, there are various places to hold electrons. And so we can hold electrons not just in the second energy level, that includes this 0 here, but also in the first energy level that includes that 0 there. So let me back up though, I digress. Let's also throw in 2 electrons here for that orbital, which means in the second energy level, we can hold a grand total of 8 electrons, 2, 4, 6, 8. But elements in the second energy level can go up to number 10 because they also include these 2 electrons here. So there's room for 10 electrons total in the second energy level. Or I'm sorry, for atoms in the second energy level because they have room in the first energy level as well. Okay, so let's expand this out. Let's make more sense of it as we go. We are going to expand out to the third and the fourth energy levels, and it's going to get kind of crazy as we go. So first off, let's go to the third energy level. That is n equals 3. So what can we do in terms of L for n equals 3? Well, we have to start at 0, and then we can go to n minus 1. So 3 minus 1 is 2. So we can have 0, we can have 1, we can have 2. These all have letters. 0 is always S, 1 is always P, 2 is always D. We can also assign some M sub L's for this. So the S sublevel is going to have 1 orbital, right? And it gets number 0. The P sublevel, I want to keep this blue, but the P sublevel can go from -1 to 0 to 1. Remember, it's negative or positive this number. That means D, if D equals 2, D can go from -2 through -1 and 0 all the way up to +2. So each one of those numbers I've just drawn can hold 2 electrons. We call those things orbitals, which means as we get into the plus and minus 1/2 thing, right? Because m sub s, you're always allowed plus and minus 1/2. So you are allowed 2 electrons in this orbital, you're allowed 2 electrons in this orbital, 2 in this orbital, 2 in this orbital, and 2 in every single one of these. You'll notice that I've gone to half arrows to make life simpler. You can do the same if you'd like. But if you count all of that up, you'll notice that you have a grand total of 18 electrons that you're able to hold in that third energy level. And we've talked earlier in a video about the progression of 2, 8, 18. Let's try this again, but we're going to go to the fourth energy level. So in the fourth energy level, get ready for craziness. N is going to be 4. When we do L, well, now we go from 0 all the way up to 3, because 4 minus 1 is 3, which means we have S for 0. We have P for 1, we have D for 2, and we have F for 3. We're not going to go there today, but remember, you just follow the alphabet after that point. If you go on to L equals 4, 5, or 6, just follow the alphabet like G, H, I. Okay, now let's assign M sub L. So remember, we got a lot going on here. We have this S is always going to be a 0, and that's for M sub L. P can range from -1 to 0 to 1, because it's plus or minus this number. D goes to 2, so we can go from -2 through -1 through 0 all the way up to 1 and 2. And then for F, F has a value of 3, so we're going to go from -3 all the way through -2, -1, 0, 1, 2, and 3. And so those are the possible orientations for those F orbitals. Remember that every single one of these can hold 2 electrons because we have spins of plus and minus 1/2. So half arrows are going to be nice for us. This orbital can hold 2 electrons. This orbital, 2 electrons. This orbital, 2 electrons. This orbital, 2 electrons. And so on as you go down the line. Every single one of these numbers represents an orbital. Every single one of your orbitals can hold 2 electrons. And so when we're all said and done, look at what's going on here. Let's count some stuff up for every one of these situations, and then we'll do the problems on your page. So if we look at energy levels in total, in the first energy level, let's do something. Let's count how many total orbitals and how many total electrons we can hold in the first energy level. So in terms of orbitals, we'll make that blue because that is the M sub L level. There are a grand total of, actually let's add one more to this in a second. There are a grand total of 1 orbital, so I'll call that O. That 1 orbital can hold 2 electrons, so that's 2 of these. And one other thing we should do is the L. L also has another name. L is called the sublevel. So there's only one value for L here, it's 0, right? So there's 1 sublevel in the first energy level. So the first energy level has 1 sublevel, 1 orbital, 2 electrons. Let's try again. Second energy level, we see 2 different letters here, 2 different numbers. So this has 2 sublevels. Look what that does for the orbitals. All of a sudden, there are 4 numbers here. So we have 4 orbitals. Every orbital can hold 2 electrons, so this second energy level can hold 8 electrons. Things are getting exponential. Let's go over to the third. In the third one, we have 3 letters, so we have 3 sublevels. We have in those 3 sublevels a grand total of, we have 9 orbitals. That does make sense. And in those 9 orbitals, we have a grand total of 18 electrons. Let's do one more. So in the fourth energy level, we have 4 sublevels. You can count up all of your blue orbitals here, right? So you have 1 plus 3 is 4, plus 5 is 9, plus 7 is 16. 16 orbitals. 16 times 2, you have 32 total electrons. And you can see there's a lot of symmetry that goes on here, right? So as you start to make some trends out of the numbers we just defined, you can see a lot of different trends and symmetry as you go up. And if this makes absolutely no sense right now, that's okay, because we're going to need a lot more work with this. Let's spend a little bit of time answering the questions on your page. So first off, it says, which quantum number describes the shape of the orbitals? Which one is the shape? Well, we are told that shape is L. So another way of representing shape for us is these letters. So L, number 1 on your note guide, is the shape. Number 2 says, how many 3D orientations are possible for L equals 2? Well, if L equals 2, let's go find that. Here's L equals 2. M sub L, the blue letters, is the 3D orientation. So 2, we said, corresponds with this one. How many letters are right here? Well, there's 1, 2, 3, 4, 5 letters. So number 2 on your note guide, how many 3D orientations are possible for L equals 2? Well, there are 5 of them, 5 possible orientations. And then finally, number 3 says, how many total orbitals are in the second energy level? Well, we've fortunately done some work already in that regard. You have 2 options. To figure out your orbitals, you can either do n squared, right? So 2 squared is going to give you 4, or if you count these up, we have 4 blue numbers. So number 3 on your note guide, how many orbitals are there in the second energy level? There are 4. So hopefully this made some semblance of sense to you. If not, no worries. We're going to dig much deeper. But this is our current understanding of the atom, and especially how the electrons behave. This is the foundation for quantum mechanics.